The barometer is a device that is used to measure the atmospheric pressure. It was invented by Evangelista Torricelli, who was an Italian physicist born in 1608. It is made of a glass tube that is filled with mercury. The tube is then inverted into a mercury basin. It is observed that the mercury falls from the tube as it is being inverted, until the height of the mercury column in the tube is equal to 76 centimeters, or 0.76 meters. Make sure that no air enters into the tube while it is being inverted. This is to ensure that an absolute vacuum exists above the mercury in the tube, or in other words, that the pressure above the mercury in the tube is equal to 0. We consider point A, which is located on the surface of the mercury basin, and point B, which is located within the tube, and at the same level as point A. According to Pascal's law, the pressure at points A and B is the same. Since point A is at the surface of the mercury basin, the pressure at point A is simply the ambient atmospheric pressure. Due to the near vacuum above the column of mercury in the tube, the pressure above the column is nearly 0. It is not exactly 0, however, since mercury has a very small vapor pressure at room temperature. But this can be neglected. The pressure at point B is equal to the density of mercury, ρm, times the gravitational acceleration, g, times the height of the mercury column, h. Since the pressure at points A and B is the same, then the atmospheric pressure is equal to the density of the liquid times the gravitational acceleration times the height. Using a mercury density of 13,600 kg per meter cubed, and substituting 9.8 for g, and substituting 0.76 meters for the column's height, we get a value of 101.3 times 10 to the power 3, or 101.3 kilopascal. This is equal to the atmospheric pressure at point A. Hence, one standard atmosphere is equal to 101.3 kilopascal. Other pressure units that are equivalent to 1 atmosphere are 1 bar, 1 torr, or 760 mm of mercury. Note that the torr pressure units were named in honor of Torricelli. If water were the liquid in a barometer, then how high would be the column of liquid that measures 1 atmosphere? And why do you think mercury, and not water, is the liquid of choice for use in barometers? First, let's find the value of H that represents 1 atmosphere of water. As we have seen before, according to Pascal's law, the pressure at points A and B is the same. Hence, neglecting the vapor pressure of water that is acting at the top of column B, the atmospheric pressure acting on point A is equal to the density of water times the gravitational acceleration times the height of the water column above point B. By rearranging the equation, we get that H is equal to the atmospheric pressure divided by the density of water times the gravitational acceleration. Now substituting in the values of the variables: 101300 for the atmospheric pressure, 1000 kg per meter cubed for the density of water, and 9.8 for g, we get that the height of the water column to measure atmospheric pressure in a water barometer would be equal to 10.3 meters. There are 2 reasons why mercury, and not water, is used in barometers. First, due to the high density of mercury, a much shorter tube can be used. The height of a column of water to measure atmospheric pressure in a barometer is, as we have just calculated, 10.3 meters. Whereas in the case of mercury, a much shorter column height of 0.76 meters is needed, which is a factor of 13.3 times smaller. Furthermore, the vapor pressure of mercury at ambient temperature is much lower than the vapor pressure of water at ambient temperature. With any liquid that is used in the manometer, the space above the liquid in the tube will always be filled with the vapor of that liquid, at a pressure that is equal to the vapor pressure of that liquid at that temperature. Hence the assumption of a vacuum above the liquid in the manometer tube would introduce a small error into the measurement of atmospheric pressure. Depending on the value of the vapor pressure of the liquid that is used in the manometer, the vapor pressure of water at 25 degrees Celsius is about 3 kPa, which would introduce an error of about 3% into the atmospheric pressure measurement. In contrast, the vapor pressure of mercury at the same temperature is only about 0.2 kPa, a factor of 15 times smaller. The open tube manometer is a U-shaped tube that is filled with a liquid and is used to measure the pressure of a gas. One leg of the tube is connected to the gas tank, or source whose pressure is to be measured. The other leg is open to the atmosphere. According to Pascal's law, the pressure at points A and B that are located at the same elevation is identical. Since the gas density is relatively low, we can neglect the pressure due to the weight of the column of gas above point A. With this assumption, the pressure at point A is equal to the gas pressure inside the tank. The pressure at point B is equal to the atmospheric pressure that is acting on the open column, plus the pressure due to the weight of the column of liquid above point B, which is equal to the liquid density, times the gravitational acceleration, times the height of the liquid column h. By setting the expressions for the pressure at point A and B equal to each other, we get the shown expression, P gas, is equal to P atmosphere, plus ρ L, times G, times H. Hence, knowing the atmospheric pressure, the density of the liquid in the barometer, and the height difference between the two manometer legs, we can measure the pressure in the gas tank. Consider the shown experiment, where we can vary the ratio of the pressure of the gas in the tank to the atmospheric pressure. The range of variation in the pressure ratio for this experiment is from 0 to 2. We can rearrange the equation we obtained in the previous section to get H as a function of the following variables: the gas pressure, atmospheric pressure, and density of the liquid. By multiplying the right-hand side by the atmospheric pressure and dividing it by the atmospheric pressure, we can get an expression of H as a function of the ratio of the gas pressure to the atmospheric pressure. Assuming the liquid in the manometer tube is mercury, we can then substitute 101300 for the value of the atmospheric pressure, 13600 for the density of mercury, and 9.8 for the gravitational acceleration, to get the shown equation for H, which now only depends on the value of the ratio of P gas to P atmosphere. 2 points are of special interest here. When the pressure ratio is equal to 0, which means that the gas pressure is 0, we plug 0 into the equation and find that H is equal to negative 0.76 meters. In other words, at a pressure ratio of 0, the manometer acts just like a barometer. On the other hand, when the gas pressure is equal to the atmospheric pressure, their ratio is equal to 1. And plugging 1 into the equation, we find that H is equal to 0. Use the slider to vary the value of the ratio of the pressure of the gas in the tank to the atmospheric pressure, and see how this affects the height difference between the two sides of the manometer's tube. When you wish to continue with the lecture, please press the play button. An open tube manometer that has a diameter of 1 centimeter is connected to a large gas tank. The manometer contains a fluid of an unknown density. 7.854 grams of water are poured into the open leg of the manometer. The pressure in the gas tank is equal to 1.1 atmospheres. If the level of water in the open manometer leg is higher by 30 centimeters than the level of the liquid in the manometer leg connected to the tank, then what is the density of the manometer's liquid? We are given that the gas pressure within the tank is equal to 1.1 atmospheres, or 111430 Pascal, and that the mass of water in the open leg of the manometer column is equal to 0.007854 kilograms. The diameter of the manometer tube is equal to 0.01 meters. And the total height difference between the surface of the water in the open leg of the manometer, and the surface of the unknown liquid in the leg that is connected to the gas tank, is equal to 0.3 meters. And we know that the density of water is equal to 1000 kilograms per meter cubed. We can start by calculating the height of the water, HW, in the open leg of the manometer. We can then use this information to calculate HL, the height difference between the unknown liquid within the open leg of the manometer, and the unknown liquid in the leg of the manometer that is connected to the gas tank. The total volume of water in the open leg of the manometer is equal to pi times the diameter of the manometer leg squared, divided by 4 times the height of water. That same volume of water is also equal to the mass of the water in the open leg of the manometer, divided by the density of water. Rearranging the equation, and substituting the values of the variables, we get the height of the water in the open leg of the manometer to be equal to 4 times 0.007854, divided by 3.14159, times 0.01 squared, times 1000, which is equal to 0.1 meters. We can now calculate the difference between the height of the unknown liquid in the open leg of the manometer, and in the leg of the manometer that is connected to the tank. That height difference, or HL, is equal to the total height difference between the surface of the water in the open leg of the manometer, and the surface of the unknown liquid in the leg that is connected to the gas tank, minus the height of the water in the open leg of the manometer. By substituting 0.3 for H and 0.1 for HW, we get the height difference in the unknown liquid to be equal to 0.2 meters. Using Pascal's law, we can state that the pressure at point A, which is located at the surface of the liquid column in the leg of the manometer that is connected to the gas tank, is equal to the pressure at point B that is at the same elevation, but is located in the open leg of the manometer. Neglecting the small pressure exerted by the weight of the gas column in the manometer tube above point A, the pressure at point A is simply equal to the gas pressure in the tank. The pressure at point B is equal to the atmospheric pressure, plus the pressure due to the column of unknown liquid above point B, which is ρ W times G times HW, plus the pressure due to the column of water above point B, which is ρ L times G times HL. Equating the expression for the pressure at point A to the expression for the pressure at point B, we get the shown equation. By rearranging the terms, we can get the shown equation for the density of the unknown liquid. We can then substitute the values of the different variables. 0.2 for HL, which we calculated in part 1 of our solution. 0.1 for HW, which we also calculated in part 1 of our solution. And then the other variables that we were given. 111430 for P gas. 101300 for P atmosphere. 9.81 for G, and 1000 for ρ W, and we get that the unknown density is equal to 4663.1 kilograms per meter cubed. An inclined manometer is used for measuring small gas pressures. Compared to a U-tube manometer, the inclined tube manometer offers a better accuracy in reading small pressure changes. This is due to the fact that a height difference, h, in a U-tube manometer is manifested as a longer length, L, along the inclined tube of an inclined tube manometer, where L is equal to h divided by the sine of the inclination angle theta. For example, if theta is equal to 30 degrees, L would be equal to twice the height difference for a U-tube manometer that is subjected to the same pressure difference. This means that when theta is 30 degrees, an inclined tube manometer is twice as accurate in measuring pressure differences as a U-tube manometer. Of course, the main disadvantage of the inclined tube manometer is that a longer tube is needed to measure the same pressure difference as a U-tube manometer.